The next speaker is Pallavi, who will present ALMA pilot study of heavily obscured quasars with young graduates.
Thank you, Francesco. Can you see my slides?
Yes.
All right, great. All right, thank you, organizers, for giving me opportunity to speak today. I'm Pallavi, and I'm a postdoctoral fellow at NRO. And today I'll be talking about some of our initial work that we have been conducting for a sample of heavily obscured quasars that also have compact radio jets. So let's get started. Just a bit of motivation. What are heavily obscured quasars? Typically, heavily obscured state in quasars can be due to orientation or due to an evolutionary effect. An evolutionary effect is when you see this very deeply dusty, heavy obscuration, because typically a quasar, we think, is typically formed by a major merger. And these early phases when quasar is just triggered and is still rapidly growing is when you still have this gas still within the central regions, and that's when you see this heavily obscured quasars. This phase is quite interesting, is because at this point, the AGN is fueling quite rapidly, and the jets and the winds that are coming out of AGN are likely to be interacting with the host, giving us some of the interesting clues into how this supermassive black hole host galaxy coevolution takes place. So how do we identify heavily obscured quasars? Since they're heavily obscured by, as the name suggests, you cannot use optical or X-ray surveys to detect them. So mid-infrared colors have been one of the efficient tools to identify such sources. So here on the right, I'm showing this WISE color plot, and you can see how different types of population are easily separated out. And just regular quasars, which are type 1 and type 2, do occupy a separate phase space, as I'm showing here in this blue circle. And typically they just have a red color only in one direction or one axis here. But this is an orientation effect, and you can find them in large quantities, in large numbers throughout these mid-infrared surveys. But when you go to this heavy obscuration or very dusty quasars, at least the ones that have been found in WISE are now, we know that they are a result of an evolution, and they are likely to be in this blowout phase post-merger. They have a quite peculiar acidity compared to a regular type 2 quasar. Their acidity in the mid-infrared is much steeper, and that's why they are easily separated out in this WISE color phase space. And this has been the way to identify these samples of dusty quasars using WISE colors. So our sample has been similar. We made use of WISE. We made sure that these sources are bright at longer wavelengths, making sure you're having this rising acidity that you expect. And they were bright and had very red colors in the WISE, as you can see here. But most of the other samples have been radio blind. And what we have done is we cross-matched our WISE selection with the NVSS. This is a VLA survey. And we made sure that we are picking out sources that have a bright and unresolved radio source. So making these sources also jetted. And then the entire cross-match was then inspected with the SDSS in the optical to make sure that these are optically faint or undetected. So this sort of additional requirement ensures that we are indeed looking at embedded dusty quasar and not a optically bright quasar. That means, if that's the case, that means you're past the blowout phase. And here is the WISE color plot again, and you can see this is our line for our sample selection. And here in the circle, I'm highlighting our sample, and as you can see, they have much redder colors than typical AGN or quasar selection. So our final sample after our all-sky search was about 156 sources. Their infrared luminosities were quite large, making them some of the luminous sources. And we had a follow-up spectroscopic redshift campaign, and we found them to be lying between 0.5 to 2.8. And that's sort of the redshift that we expect for mergers to be more common. So it's the cosmic noon is when mergers and agent activity was quite common, and our qualitative selection is in fact giving us the right redshift for these type of sources. And so why these sources are special is because we know that these WISE sources are tracing this blow-up phase post-merger, and addition of having a radio source gives us a unique window to probe jet ISM gas interactions if they are likely to be taking place. So there are quite interesting questions that you can answer with samples like these. And what I have been focusing on are two main questions: is characterizing the radio properties and also looking at the ISM content and kinematics, and also try to find this question of whether jet ISM interactions are taking place or there are any signs of that. So before I move on to the main topic of ALMA, let me just quickly tell you what I have done to understand the radio properties of this sample. The resolution of the NVSS survey wasn't good enough, and to sort of get more understanding into the energetics of radio source, we conducted a VLA survey with sub-arc-second resolution, about 0.2 arc-second. And what we are finding is that the morphologies are still very compact for most of the sources. The radio emission for about 70% of the source is still less than about few kiloparsecs or so. So we are talking about radio sources that are still within the nuclear regions or central regions of the host galaxy, as compared to the giant radio galaxies, which can go up to hundreds of kiloparsecs. And I also constructed radio spectra for all of the for all the survey or entire sample. And what we found is that about 63% of our sources have this typical curved spectra or peak spectra, which you see for compact and possibly young radio sources, in which some absorption takes place on lower frequencies in the range of few hundreds of megahertz. So overall, our VLA survey is giving us a quite good news in terms of these radio sources being very compact and possibly young. And then now moving on to slightly higher frequencies of ALMA, going to sub-millimeter region. Similar to VLA, we also conducted a ALMA follow-up snapshot survey, but it wasn't for the entire sample. It wasn't possible. So we only put in 49 sources, and this is cycle 0. So this was about 10 years ago, almost 10 years ago now. And this was done in band 7 because it felt like a sweet spot with a 1.5 arc-second resolution. And the goal was to mainly constrain the cool dust and also see if there is any either contribution from the synchrotron emission or from AGN heated dust. What we found is that about 55% of our sources were detected, and there was a significant excess in the ALMA, and sort of is giving us a sign that it's not just the AGN heated dust, but we're also likely to have a larger star formation present in the sample. This is a quite busy slide. This is a SAD ensemble comparing our sample with the typical SAD templates. But the key takeaway point here is that we did a 3-component SAD fit to get estimates on the star formation rate, AGN luminosities, and ISM masses. And here you can see on the left is that you can see those 3 components. The result of our SAD fitting for mid-infrared and far infrared data from ALMA is that SAD suggests that we have a luminous AGN, which is heating this mid-infrared dust that you see in the WISE. But also in some cases, we do need possibly a compact starburst with star formation rates of quite high, making them starburst. So, well, this is giving us a sort of a good sign that this is something that we expect in a blowout phase. We have a rapidly growing luminous AGN, and also starburst will still be going on because of the post-merger. So yes, our initial results from ALMA were giving us quite good sort of interesting results as to what's going on in the sample. But we needed to sort of move on and do some more detailed observations for at least some of our sources. So with that idea, we started our pilot high resolution observations with ALMA. So the goal was to obtain a high resolution mapping of the dust, dust or continuum emission, and molecular gas if we detect it. So we proposed for 4, but 2 sources were observed. And the goal was to constrain the ISM and also look for any signs of jet-driven outflows. And to enable this goal, we obtained a resolution that was similar to our radio imaging that I showed to you a few slides ago. It was about 2 to 3 hours per source, and here are those 2 targets, just in summary. What you see here is that one source is the nearest one. It has redshift of 0.5, and then there is another source which has a redshift of about 1.2. And what you see on the left at the top are the VLA images, and these are the 2 radio lobes. And the extension is about 8 to 10 kiloparsecs for these 2 sources. And here is the ALMA cycle 0 observation. Doesn't give much because it's unresolved. So now let's see what our cycle 6 observation are telling us. So here is a dust continuum map. It's the band 7 again. We kept the band 7 same, the observation same as cycle 0. The background images are dust continuum for the both sources, and the white are the radio contours, again overplotted here. The dust emission is turning out to be relatively compact with the extent of about 3 to 5 kiloparsecs. But it's not a simple Gaussian. We do detect we do see that there are multiple components. There is a bright core which is coincident with the radio AGN center, and it's likely to be unresolved with sizes of about 300 to 400 parsecs. And then there's a low-level extended emission along with it, which is also quite significant. This is a work in prep, so we are still trying to look more into it, but it's definitely there could be the unresolved bright core could be a starburst and not AGN, but this is something that we are trying to do with trying to figure out with our SCD fitting as well. And here is our CO line emission. Since we didn't have any prior data for how much, whether we detect CO lines, so this was actually our bonus goal. But in fact, we detected a very bright CO line for both of these sources. Here is the nearby source with redshift of about 0.5. The image in the background for both is the CO moment 0 map. And depending on the redshift, we are looking at a different J transition. And the green is again, the radio contour. So if you zoom in, what you see is it's not a simple Gaussian again. There is a bright component which is coincident with the radio center, which is a simple Gaussian. And that could be likely coming from a standard disk rotation, but we do see some sort of extended emission in the CO as well. And the same goes for this particular source. In this case, it's not a single Gaussian. The overall emission, the overall line profile can be decomposed into at least 2 Gaussian. So the CO structure is something of a more complex than just a simple disk rotation, which could be a sign of merger. And here I'll quickly tell you is the correlation between CO line luminosity and infrared luminosity between low redshift quasars and high redshift quasars. This is a relation from Corelli and Walter. And here are two of our sources. This is a preliminary work still, but the key point is that they are still within the scatter of other dusty quasars that you find at high redshift. And quickly, here are the velocity fields for one of the nearby source. the region around close to the radio center is sort of standard disk rotation, but there is some sort of extended crazy thing that's going on here, which likely to be a turbulent ISM or possibly a different component. So let's zoom into this and see the line profiles. What we find is that, as I mentioned, again, this is this nice Gaussian profile, but there are these additional components here, which are slightly offset from the line center, and have a slightly different line profile than what you see in the center. So overall, what we are seeing is that the CO line emission is resolved into more than one components. And this could be a sign of possibly a merger with a turbulent ISM. Well, I wanted to see if there's any signs of, any outflows or disturbances in the direction of the radial lobes. But unfortunately, we haven't seen anything yet. But I'll be doing some dynamical disk modeling to sort of look into this question a little bit more. And just quickly, and I'm out of time, so I'll just show you also a confirmation of the fact that these are post-merger sources through our optical imaging. This is a LBT optical image of the same source. Here are the radial contours again, and this is the ALMA moment zero map for CO. In fact, this galaxy has a companion, and if you look at the O3 spectra from the optical, it has a very broad line widths, and which is also, again, something you typically see when you have a large outflows or disturbances due to an AGN. So yeah, there's a array of observations that we have for these two sources, and ALMA pilot study is really giving us a really good insight into the molecular gas of this interesting sample of heavily obscured quasars. Since I'm out of time, I'll stop here and leave my concluding slides here, and I'm happy to take any questions.
Thank you, Pallavi, for a very nice talk. Other question? There is a question in the audience, Gayatri.
Yeah. Hi, Pallavi. Nice talk. I think I missed it, but at this redshift for the source, especially where you showed the CO726, can you also detect C1221 along with it? I didn't check the redshift properly. So can you also detect in the same observation?
CO122?
No, C1, 1 to 2. Generally, these two lines are pretty close. And if so, if you see the same profile in C1221 as well, that could be super interesting.
Yeah, that's actually really interesting. So when I proposed for these observations, I was grad student and I didn't know what I was doing.
Okay.
So I sorry about that. But
no, I mean, I was just curious. No, I was just curious. That's it, nothing else.
But I believe I'll check for C1. I was looking for HCN line for this particular source because that's something you expect. I didn't have time to talk about it, but in fact, for this nearby source, we do keep our spectral windows without me knowing that I'm doing it. I was putting it on HCN line, and I don't know if I have it, but in fact, we do detect HCN line for this particular source. So there is an additional line. It's not C1, but
no, I was just curious because sometimes if you see similar profiles and if you also see two components suggesting in two lines, maybe it could be something interesting to see. I was just curious. Thank you.
Yeah, I'll check for, and based on your suggestion, I'll check for C1 line for this particular source. As you mentioned, it might be available for.
Yeah, I think the two line frequencies are quite close, but I don't know how close they are at this redshift too. So I just have to check that. Yeah.
All right, I'll check it as well. Thank you.
No problem. Thank you.
There is another question from Maria.
Hi, thank you so much for your presentation. I come from optical kind of background. Sorry, it's my kids are back home. I was trying to understand because when you showed your original classification, was type 1 quasars and type 2 quasars, which are also with like the little astronomer icon, which are also called obscured. But then your objects are not type 2 quasars either. They're
Yeah,
actually a different class of obscure quasars.
right. Yes, so maybe this can help a little bit. Yes, so typically, when you look at their SEDs, so for example here, I hope it's clear. So the green SED would be for a typical type 2 quasar, and whereas when you look at these sources and their SEDs, especially in the near infrared optical and WISE, the mid infrared region, they are not typical. Their SEDs are slightly different, actually quite different. They are much steeper than a typical type 2 quasar. And so there is some aspect of torus present here, but it's not just a regular tori that a torus we're talking about. They are much steeper. They're much more luminous than a type 2 quasar that you would see in the mid infrared. So it's not just our sample, but there have been other samples of they're also called as hot dogs, which are dust obscured galaxies, in which this heavy obscuration and this steep, very rising SED is something that's coming out of maybe a larger scale of obscuration and not just a torus, which is very close to the AGN. So
Yeah,
the overall point is that the SEDs, you cannot use a typical quasar type 2 template to fit their SED. You need something else. And this is what sort of triggered the whole SED fitting question of these type of sources.
thank you. And have you considered to compare to other types of galaxies somehow as a control?
Yeah, that's something my the PI of this project, Carol Lonsdale, is she's going back now and looking at sort of creating a control sample and revisiting our sample selection to do some more statistical work. So that's a work in progress at this point.
Thank you so much.
Thank you.
Thank you, Pallavi. If you have more questions for the speaker, you can post them on the Slack channel.